Good morning, everyone. As we know, noise is one of the most common factors in a working environment, and over 80 million of workers complain about noise at work. So there are many ways to reduce noise in a working environment, but I would like to share with you some of my research regarding acoustic barriers with innovative way to construct them, which means we are using sonic crystals to create sonic barriers. Sonic crystals are periodic arrangement of scatterers, and the first study about sonic crystals in acoustics was performed by Martinez Sala in relatively not a long time ago, and it was started by a kinematic sculpture in Madrid. We can see this sculpture here, and it turns out that this sculpture can attenuate noise in specific frequency ranges. So acoustic study about sonic crystals was started in 1995 by Martinez Sala, and from that time other researchers and other studies was performed. So sonic crystals now are used in many solutions. For example, we can see here some solutions for road traffic noise, but also we can see some limitations because of the size of scatterers. Also, we can use sonic crystals structures for attenuate noise in railway tracks or tramway tracks. If we use this structure in proximity of the tracks, we can reduce the noise from the wheels of the tramway or train, and we can achieve a fairly good results, and these structures are effective in noise reduction. Also, sonic crystal structures could guide sound waves. For example, we can direct sound wave in specific location if we want, or even we can split sound wave in two directions if we want. So sonic crystals have also some other effects. And one of the interesting effects of sonic crystal barriers is illusion of proximity of the location of the sound. So if we have sound source behind the barrier of sonic crystals, the listeners feels that this source is close to him than in reality. And I think the most interesting characteristic of sonic crystal barriers is that those barriers can transmit light and air. And for example, if we have some machines in the industry which emits high level of sound pressure, and they also emits a lot of heat, we cannot use like enclosures and the barriers that somehow limit the airflow. So in that application, we can use sonic crystal barriers because they allow and ensure airflow through the structure. In theory, we have several lattices of sonic crystal structures, and to create unit cell of sonic crystal, we need at least 3 rows of scatterers. And the band gap, which means like a sound trap, is calculated for specific frequencies, and it depends on distance between scatterers and also depends on the size of the scatterer. So sonic crystal structures has some limitations, and sonic crystal structures attenuate noise in very narrow frequency ranges. And usually, if we use only one layer of sonic crystal structure, we can attenuate only one frequency, which is, like we see here, calculated from the geometry of the structure. To increase the sound attenuation and increase the range of frequencies, we need to find other solution. And one of the solution is create multi-layer sonic crystal structure, and that is what I would like to show you today. Here we have some examples of noise spectra of industrial compressors, and we can see that there are many of narrow band frequencies which emits high level of noise, but we can see that there are many of these narrow bands, like not only one, but 1, 2, 3, 4, or even more here. So we need to create structure to attenuate many of those frequencies. So we can try to create a layered sonic structure, but first we need to calculate band gaps. We need to create band structure for these barriers. And we can see here we have first layer, which is for high frequency, second layer for lower frequency, and we have the combined multi-layer structure for several frequencies. We can also assess the physical models by sound intensity measurements with Scan and Paint 3D system to assess how sound pressure levels are distributed in the proximity of the barrier. You can see some scattering effects, you can see some reflection effects, and it's very important to assess those barriers in that way, because if we use only the measurement of sound pressure level, we don't have the full information of how the sound is attenuated by those barriers. Here are some results of theoretical and physical models for transmission and insertion loss. So we can see that layer 1 has attenuation of frequencies mostly at 4 kilohertz. Second layer is like for frequencies from 2 to 3 kilohertz. And the multi-layered structure has wider frequency range of attenuation from 2 to almost 6 kilohertz. So here's the comparison of transmission loss and also for insertion loss. If we combine two layers, separate layers, into one multi-layer structure, we achieve not only the wider frequency range of attenuation, but also we have better efficiency of the attenuation. So the first step was to create some theoretical models, then build a physical model, and then to create a prototype of the barrier which can be used in some industrial sites. So we built a barrier with acrylic glass. This is the multi-layer structure. And we can see some frequency attenuation here for 3 kilohertz, 2.5 kilohertz, and also some regions where the sound is transmitted through the structure. And this is most important result. We have some example of a workshop with a door opened for some reason. For example, if there's too hot inside or there is some smoke inside maybe, and the door needs to be open. With door opened, we have those sound pressure levels, blue line. And if we use our multi-layered sonic crystal barrier, we can achieve attenuation of up to 20 decibels, but also ensuring the airflow through the structure. So this is very important to know that those barriers not only reduce noise, but also ensure airflow and also the light transmission through the barrier. So to conclude my presentation, we have, like I said before, many ways of reducing noise, but usually barriers or enclosures or cabins need to be firmly sealed, because any gaps, any openings create opportunity for noise to be coming outside, and the efficiency of those barriers when there are any gaps or openings are very low. So sonic crystal barriers create opportunities to create barriers or sound reducing devices, which allows to air to come through the structures, and also the light transmission. And also very important thing about sonic crystals, that they can be built by mostly any materials, because we need to create reflections. So the acoustic impedance of air and of the scatterers should be, the difference should be high enough, but we can use wood, we can use metal, we can use plastics, we can use acrylic glass, so any materials which reflect sounds will be good for the sonic crystal barriers. So that's all, and I hope this was interesting for you. Thank you very much.